Hi everyone, welcome to Unit 2 of online course on probability distributions. In the first unit, we have discussed basic concepts regarding random variables, that is, with respect to a random experiment. We have defined sample space, events, probability functions, and random variables and its distribution functions. Now we are going to discuss in this module probability density functions that will help you to follow succeeding units of this probability distribution course. And as we discussed with regard to random variables, a random variable is a real valued function defined over the sample space. So there are two types of generally there are different types of random variables, generally that are classified as discrete random variables, continuous random variables, and mixed type of random variables. But in this course, we are discussing only the distribution functions regarding discrete random variables and continuous random variables. And what do you mean by a discrete random variable? So a random variable x is said to be a discrete if the range of x is countable. That means, suppose x is a random variable that is defined over the sample space. So a real valued random variable we have, and this random variable may have either finite number of values. Suppose a random variable have finite number of values, or infinite but countable. So if a random variable having finite number of values or infinite but countable number of values, we call that random variable as a discrete random variable. So this is a discrete random variable. So this is the definition of the discrete random variable: a random variable with either finite or infinite but countable number of values. It is a discrete random variable. And the corresponding distribution function is also known as discrete distributions. So for a discrete random variable, we are going to discuss discrete distributions like binomial, Poisson, etc. For example, suppose you consider a box containing defective and non-defective items, that is, good and bad items. And if we are drawing items from the box, and suppose we define a random variable x as, suppose you have a random variable x that is defined as 0 if the item is a defective one. X is equal to 0 if it is a defective item, and 1 if it is a non-defective or good item. Non-defective. Suppose you define a random variable like this, that is, you are drawing items from a box containing both defective and non-defective items, and let us define x as 0 if item selected is a defective, and if item is a non-defective, the value of the random variable is equal to 1. So this is an example, a simple example of a discrete random variable, because this random variable have finite number of values, only 2 values. And another example, suppose you are tossing a coin until a head occurs. suppose you are performing the random experiment of tossing a coin, and we are tossing the coin until a head is obtained. So that means the observations are, the outcomes are, it may be head, or maybe tail head, or it may be TTH, etc. So this is our sample space of this experiment. So sample space of the random experiment of tossing a coin until a head is obtained is this one. And let us define a random variable x, number of trials required, number of trials required for getting a head. So if this is the situation, the value is equal to 1. If this is the situation, we have the value 2, 3, etc. So the value of the random variable x, if x is defined as number of trials required to get a head, or if x is the number of failures or the tails before the first head, and if it is like that, number of tails before first head occurs. If this is the definition of x, then the value of this one is 0, 1, 2, etc. So both are similar random variables. So if this is the situation, you can see that this random variable x have infinite number of values but countable. So the first example consisting of a random variable having 2 or finite number of values, and second example I am giving here an example of a random variable that have infinite number of values but countable. So both cases, these are the two cases where we are giving the definition, we are having the concept of the discrete random variable. So x is a discrete random variable because x is finite number of values or infinite but countable number of values. So that is an example for a discrete random variable. So the coin is tossed until a head is obtained, then this is the situation. And for a discrete random variable, we are discussing probability density function. When we are specifying a random variable with the relative, the corresponding probability values of the random variable, that collection, that is the random variable and its values and probability corresponding to each value, that collection we call as probability density function, or more specifically for a discrete random variable we call it as probability mass function. So probability mass function of a discrete random variable x with values x1, x2, etc., and that is denoted by, usually denoted by f of x, is defined as f of x is equal to probability of, this is the definition of the probability mass function. F of x is equal to probability of x is equal to x, where x have different values x1, x2, x3, etc. So that means while specifying a discrete random variable, we are specifying its values and specifying its corresponding probabilities. This collection we call it as probability mass function. And note that when we have the probability mass function f x, that probability mass function satisfying these two important properties. One is f of x is always positive because it is a probability value, and again the sum of the probability mass function, total value of f of x over all x values, is equal to 1. So whenever we have a function probability f of x that become a probability mass function, provided these two conditions satisfied, f of x is positive and sum of f of x over all x values is equal to 1. So this is the definition of the probability mass function of a discrete random variable. The example, earlier we discussed a random experiment of tossing a coin 2 times and x be the number of heads obtained. So that means, suppose we have coin is tossed 2 times simultaneously or 2 coins tossed simultaneously. So that means the outcomes are this is the sample space, and suppose we are considering x as the number of heads obtained. This is the definition of our random variable, number of heads. Then the possible values are 0, 1, 2. So these are the possible values of the random variable. Now our aim is to find the corresponding probabilities that we discussed in the first unit. That is, probability of what is the value x is equal to the first value 0. Probability of x is equal to 0. And that is obtained by, this x is equal to 0 means this is the possibility. When outcome is TT, then only x can have the value 0. So that means out of 4 cases, we have only one favorable, that is 1 by 4. And probability of x is equal to 1, next value of random variable is 1, x is equal to 1. And that value is equal to, there are 2 favorable cases out of 4, because these are 2 favorable cases for the value 1, because only one head is obtained if it is TH or HT. So there are 2 favorable cases out of 4. Similarly, last value of random variable x is 2. This is equal to 1 divided by 4, because only one case is favorable for 2 heads out of 4, so 1 by 4. So that means when x is equal to 0, 1, 2, the corresponding probability values are 1 by 4, 2 by 4, 1 by 4. So this collection, this random variable values and corresponding probabilities give us the probability mass function of this particular random variable. So this is the case. This table or the value giving the probability mass function corresponding to different values of x. This is our probability mass function of the discrete random variable x. And another example of similar to this one, suppose you are considering tossing of a coin n times, a general situation. So toss n coins simultaneously. So sample space consisting of, the last case we had tossed 2 coins. So it is n coins are tossed. So total possible cases are 2 power n. So there will be 2 power n possible cases. So out of 2 power n possible cases, suppose x is the number of heads we define, the random variable x is number of heads. Then each of this 0, 1, 2 are the possible values, and corresponding to 0, 1, 2, etc. up to n, favorable cases are NC0, it may be NC0, or it may be NC1, or it may be NC2, etc. up to NCn. So corresponding the values of 0, 1, 2, etc. up to n, the favorable case are NC0, NC1, NC2, etc. up to NCn. So the probability of getting x is equal to x, that is probability of x is equal to x, is equal to NCx divided by 2 power n, where x is 0, 1, 2, etc. up to n. So this is the general case of the last example. So earlier we have an example of tossing 2 coins. Now we have the example of tossing n coins simultaneously, and the probability mass function is given by Ncx divided by 2 power n, where x is equal to 0, 1, 2, etc. up to n. And this is a similar example, that is when we have tossing 2 dice simultaneously, and x is the number of sum of the upturned faces, then the probability mass function of x is given by the values of the random variable. We know the outcomes are, when we have tossing 2 coins, we have the outcomes like this. So, these are the possible outcomes when we are throwing two dice simultaneously, and let x be the random variable defined as the sum of the phases. Then if this is the situation, we have 1 plus 1, that is 2, 2 plus 1 3, etc. up to 6 plus 6 12. So, the possible values are 2 to 12, all the values from 2 to 4. And corresponding probability mass function values we can calculate from this sample space. How many are favorable to the each value? X is equal to only 1 is favorable out of 36 outcomes. So, 1 divided by 36, and when x is equal to 3, that means sum is equal to 3. The favorable cases are this are the two favorable cases. So, there will be 2 cases out of 36. So, 2 divided by 36 like this up to suppose x is equal to 12. There is only one favorable case, that is 6 6. So, 1 divided by 36. So, collection of the random variable value and corresponding probability mass function value give us the probability mass function of the discrete random variable x, which is defined as the sum of phases when we are throwing two dice. So, these are the some simple examples of the discrete random variable, and not that the probability mass function or density function of discrete random variable tells us how likely our probable each of the values of the random variable is. So, that is the aim of finding the probability density function or probability mass function. It also enables one to calculate the probability of events described in terms of the discrete random variable. That is, we have the random variable values, and we are in a position to calculate the probabilities of events in terms of the discrete random variable. Also notice that for any discrete random variable x, f of x can be obtained from f of x and vice versa. That is, suppose f of x is small f of x is given, that is the probability mass function is given to you, you can find the f of x, and earlier we defined the f of x definition as probability of x less than or equal to x. So, this is very simple to calculate the probability distribution function or cumulative distribution function of a discrete random variable if the probability mass function is available to you, or if the distribution function is available to you, you can find the probability mass function also. So, when x is a discrete random variable, it is very easy to calculate the probability mass function and corresponding probability distribution function. If the distribution function is given to you, you can calculate the probability mass function also. And second category of random variable is continuous random variable. So, if we have defined the discrete random variable, if the random variable have finite or infinite countable number of values. Now, we have different situations. There are a lot of situations where this is not the case. So, that type of random variables are known as non-discrete continuous random variable, and a non-discrete continuous random variable x is said to be absolutely continuous or simply continuous if its distribution function, that is capital F of x that we defined earlier, that can be represented in terms of a function f of x. So, suppose you have a distribution function of a random variable that is given by integrating a function f x from minus infinity to a real number x, and if that is the situation, we call the random variable x as a continuous random variable and this f of x as the probability density function. So, that means a function, suppose you are given a function f of x, suppose we have a random variable x which is continuous, not it is a discrete continuous random variable. That case we have the function f of x, suppose, and that f of x can be this is the cumulative distribution function of x, distribution function of x, and that can be written as integral from minus infinity to x sum the function f this one, where x is minus infinity to plus infinity, any real number. And this effect satisfying properties 1, this fx is always positive, fx is always positive. And 2, suppose we are integrating the fx over all range of values, that is equal to 1. And third one, if we are integrating the value fx from a to b, then that is nothing but probability of a less than x less than b. So this the f of x, that is probability density function that we discussed earlier, satisfying these 3 properties. One is non-negativity, and second is the total value integral from minus infinity to plus infinity, fx dx is equal to 1. And suppose you are integrating the density function from a to b, then that is nothing but probability of the random variable x lies in between a and b. And note that this, for a continuous random variable, probability of a less than or equal to x less than or equal to b, or probability of a less than or equal to x less than b, or probability of a less than x less than b, less than or equal to b, or probability of a less than x less than b. See these 4 situations. For a continuous random variable, this one, all these 4 probabilities are same, because for a continuous random variable x, the probability of taking a single value, that is, let it be a, that is equal to 0 for a continuous random variable. So the probability of a less than x less than b, or a less than or equal to x less than or equal to b, or this one, are same as integral from a to b fx dx. So this is the property, these are the properties of density function of a continuous random variable. Also remember that if f of x, that is the distribution function, is absolutely continuous, and f of x is a continuous function at x, we can find the probability density function by differentiating this. So for a continuous random variable, how do you find the probability density function if the distribution function is a variable? That is a question. So if the distribution function is a variable, and if the probability density function is continuous at x, we can find the value of the probability density function by differentiating the distribution function with respect to x. And some examples also we can note here. So suppose you have a continuous random variable, x have the probability density function, this one, that is f of x is equal to x, 0 less than x less than or equal to 1, and 2 minus x when 1 less than x less than or equal to 2, and 0 otherwise. So you can see this is a probability density function. Why? Because this f of x is always positive. Again, integrating the f of x from 0 to 2, that is the range of values of x value here, that is equal to 1. We can easily establish that integral from 0 to 2, integral from 0 to 2 fx dx is equal to 1. Okay, f of x is positive. So since these 2 conditions are satisfied by this function, this is a probability density function of a random variable. And the question is how to find the distribution function. And to find the distribution function, we have the distribution function fx, this is equal to probability of x less than or equal to x by original definition, or integral from minus infinity to x fx dx, because x is a continuous random variable, and our aim is to find the probable distribution function of that particular random variable, and that is the random variable you are given as fx is equal to x when 0 less than x less than or equal to 1, and 2 minus x when 1 less than or equal to x less than 2. So, this is given to you. So, how do you find the distribution function f(x)? That is our problem. How to find the distribution function? So, to find the distribution function, first of all you consider the x value is suppose in between 0 to 1, case 1, because you are given the function is like that. So, when x is in between 0 to 1, what is our capital F of x? That is the distribution function. That is integral from the lower limit here is reduces to 0 and x, and in this range the function value is equal to x. So, x dx, and integrating this become x square divided by 2, that is from 0 to x. So, the value is equal to x square by 2. So, when x is in between 0 and 1, the distribution function value is equal to x square by 2. Now, the second situation is when x is in between 1 less than or equal to x less than or equal to 2, what is our f of x? Again, the f of x is given by integral from minus infinity to x fx dx, that is our basic definition. And how do we find this value? This is equal to, here the lower limit is 0 again. Remember, the lower limit is 0 because the random variable x is in between, the values are in between 0 to 2. So, lower limit is 0 to 2 x fx dx. And we have to split this integral into 0 to 1, because the function is defined like this, 0 to 1 plus 1 to x, because x is a value larger than 1. So, 1 to x, and that is equal to integral 0 to 1. In this range we have the function value x plus integral 1 to x. This range the function value is 2 minus x, and simplifying we will have the integral of this is x square divided by 2, and the range of values from 0 to 1, and for this function integrating we will get 2x minus x square divided by 2, that is from 1 to x. And substituting the limits, we have this is 1 by 2 plus this is 2x minus x square by 2 when upper limit is substituted, minus 2 minus 1 by 2. So, that is this is 3 by 2 plus 1 by 2, that is 2x minus x square by 2 minus 3 by minus 1. So, simplification gives us the value 2x minus x square by 2 minus 1. Hence, our distribution function fx is equal to x square divided by 2. See, 0 when x is less than 0, and x square by 2 when 0 less than or equal to x less than 1, and earlier we have 2x minus x square by 2 minus 1 when 1 less than or equal to x less than 2, and 1 if x is larger than or equal to. Yes. Previously we have okay. This is the capital F of x. So, this is the way we can find the value of f of x, the distribution function, if the f of x is given to you. Another example, that is, you have given the distribution function f(x), and that distribution function is given as this one by 2 x by theta plus 1 from minus theta to plus theta. And here the reverse order we are finding, that is, if you find the probability mass function, and probability mass function, this is a continuous random function, you have the f of x is given by differentiating the value of the distribution function. And that is equal to, when you are differentiating, you will get 1 by 2 theta as the value, that is from minus theta to plus theta. So we are differentiating this expression, you get the value 1 by 2 theta. So that means you can find the distribution, probability density function when the distribution function is given. So these two examples established you that if you are given the distribution function, it is possible to find the probability density function, and if the probability density function is given to you, it is possible to find the distribution function for the continuous random variable using this technique. So next module we are going to discuss some important special distributions and its mathematical expectations, variance, moments, moment generating function, etc. So we are wind up this session. Thank you for listening. Thank you to all.